Right, so here's an example of a graph with error bars. In this case it was that we had some masses, different masses were accelerated, different masses were rolled down a slope and the accelerations were measured. And so we generated some data. You can see 6 or 5 points on the graph, and after an initial graph was plotted, the initial graph looked something like this when just simply mass was plotted against acceleration, and that of course tells us that most likely acceleration is proportional to 1 upon mass. So then we plot a second graph to try and get a linear graph with indeed acceleration on the vertical axis against 1 upon mass on the horizontal axis. So we transform all the mass data by taking their inverses, 1 upon each number, to generate this axis here. And when these points are plotted, you can see we get a nice straight line relationship. I just move these out of the way a bit to make it clearer. So this graph now, about this graph, well, a couple of features you need to pay attention to. This is a real origin here. You can see the scale starts and goes up in 2s, 2, 4, 6, 8, and so on. And in this direction, it's also even, starting at 0, going 1, 2, 3, and so on. That means we can actually read off our y-intercepts directly from the graph, from where they cut through the axis, which saves us a bit of work. This is not always possible, and this is not always necessary, of course. You can use the y equals mx plus c equation to solve for the y-intercept if you can't start the graph and fiddle the points nicely to make a big graph. The two lines, you can see the best fit line, which is in solid, averages through the points quite nicely, and then the error bars are plotted for both the mass, or 1 upon mass, and for the acceleration. The vertical bar is the acceleration errors, and the horizontal bars are the error in 1 upon mass. Now you don't have to put both horizontal and vertical. In most cases it's okay just to put the bigger error bar. In this case it looks like for most of these points the acceleration, the vertical bar, is the bigger one. So you can still generate the error line, m dashed, the dotted line, just by going through the uppermost point here and the lowermost point here of the error bars, the vertical bars. And that would give you a good error line, as is shown here. So once you've got the error line plotted and the best fit line, what's the next step? Well, the next step is to calculate the gradients of the two lines. So here's the gradient calculation for the best fit line, we're calling it m, and here's the gradient m dashed for the error line. You can see I've just chosen 2 new points, that one there, and it looks like I've chosen this point here, those 2 points, yep, and found this answer for the best fit slope, 0.0869. Pays to keep about 3 figures for this calculation, since most of the data is generated with 3 figures. In a similar way, for the error line, I've chosen this point here, and also I think I've chosen that point logically, nice and easy. Calculated this as the gradient, 0.0792. So the difference between these two numbers is calculated here, and that is the error in the gradient of the best fit line. It works out to be to 1 figure. Remember to always round it to 1 figure, 0.008. we write our final answer here. The gradient is 0.087 plus or minus 0.008. Notice we had to lose the third figure. The 869 cannot be used. We have to round it to match the decimal placing of the error, which is the third decimal place. Okay, 0.008. So that 7 we're not certain about. So we can't have 69. Notice also the units are correct. This is per kilogram, or 1 over kilogram, because it's 1 over mass. This is still the same, meters per second squared. So now we need to find our y-intercept. Now you can see it's clearly negative 0.4, and the error line comes through at negative 0.2. So we can write our y-intercept as follows. It equals negative 0.4 plus or minus 0.2. Now it's not just a coincidence, of course. This is in fact the difference between these 2 points, okay, on the graph. It happens to be exactly 0.2, which looks like the same value as the error line, just by chance. But that is how you calculate this figure. It's the difference between the two intercepts of the two lines. Just like we found the error for the gradient as the difference between the two gradients. Rounded to one figure, must be rounded to one figure, and this is why we must round that one to the same position or decimal place as that error exists. So we can't have 0.40 or anything else because of that rule. We must match the placing of the one significant figure of the error. So that's our graphical analysis complete. The next step is to write the final mathematical relationship using the gradient and the intercept, and that happens on the next page in the conclusion. So in your conclusion, you would start with a statement pretty much the same as this. The acceleration A is related to the mass m according to my data by this equation. And now you'd write down the equation. So you'd write A equals the gradient you just calculated, okay, which happens to be 0.087 plus or minus 0.008 multiplied by the independent variable 1 upon mass. Now in this case, I'll just write it down here. We are going to add on our y-intercept, which happens to be negative 0.4 plus or minus 0.2. So that's how our equation is written. Now to get at least this much done is what is required to get achieved in the internal investigation. After this, to get merit or excellence, you need to write a good discussion that talks about how your relationship is matched or not matched by the physics theory presented in the assessment. Usually you'll be comparing some constant somewhere, and that way you can work out how valid your data is, and talk about errors and what may have affected your data to produce the results that you did. So that's the next step. But to get at least this much done, the conclusion and the equation, okay, you need this much to get achieved.